is to bend the air. There is no way you can get lift without taking the air that is coming at you, bending it downwards, and in so doing, getting lift upwards. That's the way it happens. There is no other way. All heavier than air aircraft do that. Here's another example of an airplane bending the air. Now this is a crop duster, and you can get an idea of just how much disturbance the aircraft creates as it goes through the air. We don't see this again, but you look at the traffic pattern of like San Francisco airplanes flying in, they're all doing this. And finally, here's another example of an airplane bending the air. You can see that it's making a track behind itself, and there's air rushing down and clearing out this cloud layer. And so what happens when you try and bend the air, and I'm going to use an example here with my little airplane. So, oh, excuse me, thank you. When you are going really fast, you don't have to bend the air very much. So you're kind of flying like this. The air is bending a little bit over, but you're okay. When you want to fly slower, you haven't gotten any lighter, you have less air to work with, you need to bend it more. And the way you do that is by angling the airplane further up into the air so that the wings bend the air more downwards. And that angle is called the angle of attack. At some point, when that angle of attack becomes high enough, the air will refuse to bend. It just doesn't want to follow the wing anymore. And what happens then is it differs between airplanes, but in many airplanes, it's kind of a sudden thing, and the airplane sort of falls down and drops. So that is kind of dramatic, but we learn how to recover from that, right? Put the nose back down, add power, get the airplane under control, don't have the elevator fall off. Right, better. So we learn how to control that. The more insidious thing is what happens if you are flying into the air and you stall, but you're not pointed straight at the air. And airplanes are supposed to be symmetrical, but they actually aren't, because the propeller is turning one way rather than the other, and sometimes you're turning, and sometimes you're all kinds of stuff. So sometimes you're not pointed straight into the air. And what happens then is that one wing stalls before the other. That wing drops dramatically, the airplane almost goes inverted. It then goes into a circular pattern, crashing like a stone, and interestingly enough, this is a stable pattern. The airplane will keep doing that unless you do something about it. And the amount of time required to figure out what's going on and the height that you lose by the time you figure out what's going on and fix it can be quite significant. So if this happens in a traffic pattern around an airport, it is universally fatal. And very, very dramatic, and people fall into this problem all the time. So that then is the problem of loss of control due to stalls and stall spins that we're trying to solve here. All right? Any questions about this so far? All right, thank you. So let us talk about the relative wind. So the relative wind is what you feel if you're driving along in a car and you stick your head out of the window and you hang out your tongue. If you happen to be a dog, that's very common. For most of us, we don't do the hang out our tongue part, but that is the relative wind. It's the wind that you feel if you imagine yourself stationary in the airplane and the wind is coming at you. And because we're pilots, we like to consider that point of view because it's much more easy than thinking about ourselves zooming through the air. They're equivalent. The single most important work about how to control small airplanes is Stick and Rudder. It's a book written in 1944 by a gentleman by the name of Wobegon. In 1944, the aircraft as we know it now, the general aviation aircraft, was done being invented. Nothing new in the control of small airplanes has been done since then. And in it, if you read through the book, the thing he mentions that is most important is the so-called relative wind. He talks about controlling the relative wind, being aware of it, being aware of where it's going, and he tries to explain it with a bunch of little visual aids. So he says, imagine that there's a pennant on the end of the airplane. That'll be your relative wind. Now while you're flying, think about that. He tries to show you the arrow of the relative wind. The wind is not where your airplane is pointing, it's where the wind is coming from. He tries to show you this with a little windsock at the top of an airplane. Now, it turns out the relative wind is describable by 3 quantities, and it's important to get, discuss what they are so we can have a common vocabulary. So the angle this way is the angle of attack. The relative wind might come from the side. That angle is the so-called angle of yaw, or angle of side slip. And then there's the strength of the relative wind, which we call the indicated airspeed. So these 3 parameters describe the relative wind. Now the question is, if I'm sitting in an airplane, how do I know what the relative wind is? Well, it turns out I can't see air. It's kind of a problem. So, in most airplanes, you will see some combination of these instruments. There's the indicated airspeed meter, which tells you how fast the relative wind is going. It's easy enough. There's usually a ball mounted inside of a little tube, kind of like a spirit level. So that ball is supposed to measure your angle of side slip, but actually it doesn't. It measures your sideways acceleration. By so doing, the slower you go, which is where angle of side slip becomes more of a problem, the less effective this thing is. In fact, it's less effective according to the square of your speed. So if you're at 100 knots, it is 4 times as effective as it is when you're going at 50 knots. Which is kind of a problem. And finally, the angle of attack, which is arguably the single most important parameter in controlling an airplane. And yet only recently we have meters to measure the angle of attack. And when we do, they're usually a bar chart. Something very coarse-grained, like, okay, this is the good area, this is the bad area, which just doesn't seem to fit for something that's so important. People who fly gliders have a solution to this. So they have a so-called yaw string, which is a piece of yarn that they tape up to the canopy. It tells you your angle of side slip very reliably by directly measuring the airflow. Some gliders go one step further and they have a so-called side string. So they have a string on the side that measures their angle of attack. The reason we can't do this in most airplanes that we fly is because the propeller is creating this huge, massive whirling flow around the fuselage. And so you cannot actually measure these things near the fuselage of the airplane. You have to measure it out here on the wing somewhere. And then you have the problem of, okay, if I measure it out here on the wing, how do I get it into the cockpit? How do I represent it? Do I use some system of levers or mechanical things or hydraulic things or pneumatic things, or what do I do, right? So these were problems back in 1944, but they're not problems any longer because, we can do this thing now. We can, we have computers and stuff, it is after all 2016. So that explains sort of like the technical part of the problem. Now there's another part of the problem. Who here is familiar with Lake Wobegon, Minnesota? Awesome. Okay. So for those of us who live in the Midwest or have lived in the Midwest, Lake Wobegon is a fictional town that is used by Garrison Keillor in his radio program, A Prairie Home Companion. It is the setting for a lot of his stories. And there are 3 important things to know about Lake Wobegon. It's where all the women are strong, all the men are good looking, and all the children are above average. What Garrison Keillor doesn't know is that Lake Wobegon actually has an airport. It's on the charts. KWBG, you can find it. And you know what's interesting about that? All the pilots are above average. All too many of us are from Lake Wobegon. We think that the problems that happen to average people are not going to happen to us. And the reason is that when we train for them, we're always prepared. Our instructor says, can you demonstrate a recovery from a stall? Of course I can. Because all I'm thinking about right now is recovering from a stall, right? But it turns out that when problems sneak up on you, when you're not expecting them, even the best of us make the worst and dumbest mistakes. It is really important for us, I think, to have the humility to accept that and to seek solutions, and not to say something which a lot of people in the aircraft, or the general aviation industry, unfortunately say, which is, I don't need this, I'm just too good of a pilot. I don't need solutions. I'm never going to make that mistake. We are going to make that mistake. The people who are crashing the airplanes and who have loss of control problems, they're not some bad pilots out there, they're us. And there's an interesting significance to that, which is that the National Transportation Safety Board is on our tails. So we show up for loss of control on their most wanted list for several years in a row now. And if we don't fix the problem ourselves, someone else is going to come in and fix it for us. And you know, I get it. Like, people are worried about safety in general aviation, leading to, like, your airplane will be like, it'll cost $1 million and it'll fly at 75 knots and it'll totally suck and it'll be all airbag. And any space that's not taken up by airbag will be all parachute. But really, I mean, we can solve this problem without having to go that far, and our solutions will probably be less in that direction than the solutions that someone else imposes on us. So I think we just need to come up with ideas. And to that end, then, I have my proposal for a solution. Now remember, as Beth pointed out, and that is very true and important to keep in mind, this is a work in progress, right? It is not the solution, and it may not be the final form of this solution, even if it's adopted widely, may not be exactly what I'm showing you today. There are a lot of smart people in the world, and I hope that they help develop this better. All right, so let's go back to the relative wind, and if you don't mind, I'm going to put down my mic for a while. The airplane, remember, the relative wind is described by three things: the angle of attack, the angle of side slip, and the speed or strength of the relative wind. The idea of my solution is simply to imagine that you're sitting in the airplane and you can see this arrow. It moves left and right and up and down with the relative wind, and as the wind becomes stronger, it becomes bigger, and as the wind becomes weaker, it becomes smaller. And so we end up with an instrument that looks like this. Since this is the title of the talk, you probably know that this is called Airball. That is what I'm calling my instrument. Let's pick up the mic again. So, this ball has a diameter that's proportional to the indicated airspeed. For the cognoscenti, this means that the area of the ball, which is what your eye perceives as like the bigness of the ball, is proportional to dynamic pressure, which is what actually creates lift. It moves up and down with angle of attack, so as the angle of attack increases, the air is coming from below, so it moves down. And it moves left and right with side slip. There are a bunch of annotations that we've come up with to put on this display. This is your reference angle of attack for and landing approach. This is, because it looks like ramps, this is your best angle of climb, angle of attack. This would be your best rate of climb, angle of attack. And this we call the cow catcher. This is where you don't want to go. This is your stall angle of attack right there. So let's talk about what it looks like at different flight conditions. So first of all, this is an example of a primary flight display that would include all of this information, plus some extra things about altitude, rate of climb, and also if you want a speed tape. Notice this is all air data. I can draw this with just air data. I'll return to this, the significance of this kind of display in a minute. But for now, just bear in mind, we can do this. Now, here's an example of this of the airball display in cruise. So the ball is nice and plump. It's at a relatively low angle of attack, and you're pretty much coordinated. You can see you're a little bit off, but you know, you're not too much off. This is an example of the airball when you're landing. Again, you're pretty much coordinated. You're not pointing left or right. The airball is a little smaller, and you're right in the middle of the cups. This is an example of the fabled base to final stall, and I've talked about that before when I showed you the problems at the airport. So here, the airflow is coming from the right because you're using rudder to turn left, and it's coming from below because you're at a high angle of attack, and it is also small because you're going slowly. And this is where people making a left turn base to final, that's where they break their airplanes. That is what will lead to a spin. And this is another kind of condition, and it demonstrates something interesting. So this is approaching an accelerated stall. Here I'm going fast, but I'm pulling a lot of G's. And what you can see here is that this tells you more than an angle of attack indicator tells you. You can see that the speed is very high, and you can also see that your angle of attack is very high. You would not be able to see this and sort of mentally remember this picture if you were just looking at angle of attack. And the important thing to keep in mind here is every one of these things I've shown you is like a snapshot of a certain flight condition. And you can remember this right away and be able to just recognize it when you see it. Just at a glance, you can look at it and say, that's where I'm going. And that's much better than having to see these 2 or 3 or 4 different instruments all over your panel that you have to chase around. One of the things we've thought about extending this with is putting a true airspeed ring around the ball. That would give you kind of an idea of your indicated to true airspeed spread, which might give you an idea of your density altitude. I put this here simply to remind us that this is a work in progress and it's not finished. And there are all kinds of things we can add to or remove from it or change. And finally, back to the PFD. A lot of people are building small, inexpensive aircraft, usually experimental aircraft. The first thing they do is put in there is an artificial horizon. Even though they're never going to fly in actual instrument conditions, they're actually not going to ever fly into clouds. And if I had a certain number of dollars to spend on instruments, I would much rather see the thing that I can't actually see by looking out the window. And that is the actual air data. So if I had my druthers, a simple experimental aircraft with just one instrument would look like this. Now there's one final point which I think a lot of people might ask, which is, I'm giving people the raw data, the angle of attack, the angle of yaw or angle of side slip, and the indicated airspeed. Is there a way to cook this data in some way that gives you a single view that tells you, are you okay or are you not okay? And as hard as I've thought about it, and I don't claim to have the conclusion, but as hard as I've thought about it, I don't have that insight. And that goes back to the diagram I showed you about when people are crashing their airplanes. Remember, 41% was during maneuvering flight, which is a very general kind of set of conditions where there's no single rule of thumb about what is good and what is bad. So the conclusion I've come to is that the best we can do is just give the pilot this raw data and allow them to do what humans are awesome at doing, which is recognize patterns and adapt to them. So now I'm going to talk to you a little bit about early testing of this system, and then we're going to talk more about the prototyping that we're doing moving forward, and also how we're spending the $25,000 we got from the EAA. So one thing we've done is we've created a simulator with an Android tablet, and we've tried it out, and a bunch of people, including a few friends of mine who are very skilled flight instructors, have thought that it was interesting and worth looking into. With any luck, we'll get this simulator working for you today, but the gremlins of technology are always, alive, so we'll see what we can do. Another thing is that Dynon instruments are actually equipped with a way to get the air data out of the instrument using a simple cable. So we've been able to get an Android smartphone into my friend's RV9A experimental airplane and actually fly with this thing. And finally, this is my friend Paul Eastham, who built the RV9A. This is him using Google Glass. And it's actually an interesting idea to think about putting situational displays like that on head-mounted displays or things that are very close to the pilot's field of vision. It so happens that Google Glass turned out to be abysmal because the brightness was nowhere near what you would need for going around in a cockpit environment with bright sunlight. But it points to some interesting future directions. And you know, I think maybe that would be something to investigate in the future. This is a YouTube video of some of the testing we've done, and can you play the video? Is it possible, Tom? You should be able to just click on it. Yeah, maybe go back into presentation mode and play it. Yeah, if it doesn't work, don't worry about it. I can show it later. Yeah, is it not working? Okay, Gremlins, no problem. Oh wow. Uh-oh. Nope, all right. We have tested it. Trust me, I would not lie. Okay, well let's just move on for now, and we can see if we can show it later. Present up there. Yep. What you don't know is that I have a really weird eraser head mouse set up on this laptop, and so Tom is a hero for doing this. Okay, so can we go to the next slide then, please? Oh, right, sorry. Ha, okay. So one of the challenges of this project is actually measuring the air data. So I'm going to do a very brief overview of how we're measuring the air data. This is sort of for the hobbyists among us, but I think anybody can really follow along. It's not really rocket science. So in flight testing, like if you're NASA, you build these really complicated probes to measure all the details of the airflow on an airplane that you're testing. These, as you would imagine, cost many, many thousands of dollars. We don't have many thousands of dollars. This is another example of a somewhat simpler probe called a 5-hole probe. So basically what people do is they make 5 holes, a central hole which measures how fast the air is going, and then 2 holes up and down, and 2 holes left and right, and depending on how much you're skewed into the air, this tells you by measuring the pressure difference how much you're skewed. In order to understand 5-hole probes, you have to understand how the flow of air works around a sphere. So it turns out I have a friend, Julia Pantaloni, who's a brilliant aerodynamicist, who tells me that this math actually works. That in the regimes in which we do our work, this is a good approximation. Forget it, it's just math. We're moving on. So this is the situation that we plan to build. So imagine this is a probe. This is the angle of attack, you can see. And we're measuring, first of all, a pressure we call P0, which is the pressure in the center hole. And that is the difference between that pressure and the pressure at a static source. You will recognize that that's exactly the pressure that your airspeed indicator measures. In fact, your airspeed indicator is just a pressure gauge that's calibrated in knots or miles per hour. We also measure the difference in pressure between the top and the bottom holes and call that PA. And then we take the ratio of PA divided by P0. It so turns out, just because it works out that way, that PA divided by P0 at all altitudes, at all airspeeds, at all densities, at all conditions, is a predictor of angle of attack, according to this curve. And at about 15 degrees angle of attack, we get a ratio of about 1.3. So it's actually a very good solid signal. And in fact, you could do worse than just draw this as a straight line. Now, obviously, we're going to have the actual curve in there, but it's really a very simple correlation. So that is basically the theory behind our air data probe, and we'll show you more of it as we go along. In fact, I'm going to talk about it right now. So the probe that we're trying to build is something that is simple enough that someone can stick on the strut of their aircraft and not have to talk to the feds. And so that means basically make it work and look like a GoPro camera. Make it battery powered, make it independent, make it talk wirelessly to whatever it is you put in the cockpit, and just avoid regulations as much as possible. For experimental aircraft, of course, you can do whatever you want, you can rivet anything to your airplane, but that would be very limiting. What I would really like is something that I can give to someone who flies a Citabria and say, dear Citabria flyer, please bolt this onto your strut and fly around for a while and tell me what you think. And so the idea we're coming up with, and there are some parts over there that you can mess with once this talk is over, is something using 3D printed parts, polycarbonate tubing, aluminum tubes, and really cheap sensors. It turns out that to measure the pressures, we need these pretty high quality sensors, and those are actually the biggest contribution to the cost of our bill of materials. They're about $50 a piece, so anything from $40 to $60. And we're going to need 3 of them. For measuring barometric pressure, it turns out you only need to spend $10. This is so common that they're just these parts that are just laying out there. Temperature probes are about $25, and a little computer to take all of that crap and send it over to a smartphone, literally $5. So we think we can build this pretty cheaply. We may eat our words, because aviation is a very unforgiving environment, and we will find out the ways in which our cheap solutions are inadequate. But one thing to think about as well is a lot of avionics are built targeting the most difficult case. Like, they're usually built to be ice resistant, they're built to be damage resistant, etc. Not everybody in the world needs all that fancy zoot. And so if we can make something for a Cirrus that costs $3,000, and at the same time make something that works the same that someone can put on their ultralight that costs $300, then maybe that's a good compromise. And eventually what we'd like to do is to have a display that's actually bright enough to work in a cockpit, but for our initial prototyping, we're just going to try and use a smartphone. So now I'm going to talk a little bit about the relationship of this to training and thoughts about flight training in general. So this is a sports coach. When the players are in actual competition, they usually have their coach right next to them. Even though 99% of the work of a sports team is done in practice. But the presence of the coach reminds you that all you have to do is do it just the way you did it in practice. So in a sense, practice is, in a sense, the competition is just recreating what you did in your practice. The same is true of orchestras. Orchestra conductors are there when their orchestra is performing, even though 99% of the work they do is during rehearsal. Things are different for pilots. Once we get our license, we jump in the cockpit, and we're all on our own. And I claim that that is a little bit dangerous. If I had my druthers, if I could afford the weight penalty, if I could afford the money, I would have my flight instructor sitting with me every time I go and fly, for like the first 500 hours of my flying. Because you know, why not? Because they'll watch me, and they can, sorry, batteries are coming out of this thing. So they can watch me, and they can help me prevent the mistakes that they have seen me make over and over and over again. So I think for aviation, just because of the fact that we don't have all of these people available around us while we're flying, it is crucially important to take the training environment and bring it into the cockpit as much as possible. Another thing to think about, the average American drives, somewhere between 10 and 12,000 miles a year. That's 300 hours behind the wheel. How many of you here fly 300 hours a year or more? You do. Excellent. Sir, you married very well. For the rest of us, we don't. And in fact, when you think about the 300 hours you spend behind the wheel in a car, this is actually pretty high quality training. Because people are cutting you off, you're hitting potholes, you're hitting exits and entrances, and you're stopping at stoplights. Whereas in aircraft, a lot of our flying is during cruise, when basically we're buzzing along, everything's hunky-dory, nothing's happening. And you see that in the statistics. Maneuvering flight, takeoffs, and landings. Other than that, people don't lose control of their airplane just when they're flying around on a beautiful day. They just fly around and it's fine. So these 300 hours of driving practice are actually rich, dense, practical experience in driving that we don't get when we're flying. So basically it means the burden is so much greater for us pilots. And the hope of the solution that I'm presenting to you today is that this is a way for you to remember the picture of what things looked like when you were practicing a maneuver. The picture of what it looks like when you're landing. And it gives you a holistic view of all that is going on in the most important part of your airplane's flight, the relative wind, that you can then carry with you into your practice and use it as a training aid on a daily basis. And in so doing, basically tighten the feedback loop around training and practice as much as possible. Because once again, as Wolfgang Language told us, you have one job as the pilot of an airplane. It's to control the relative wind. We don't fly airplanes that have rocket engines. So the only way we can get the airplane to go where we want is to control the relative wind. And every loss of control of the type that we're talking about here was preceded causally by a loss of control of the relative wind. There simply is nothing more important in flying an aircraft. So at this point, thank you very much for coming. I would really welcome any comments and reactions you guys have, and please feel free to email me if you're interested in trying this thing out once we have prototypes. And also, please follow us at airball.aero. Right now this site is organized as a blog, but we will be adding content to it, and you can watch what we're doing and all the stuff we're trying to invent. And please, after the talk, please do come over and check out what we have here. I will try and get the simulator working, and meanwhile you can just see the little parts we have and all the little ideas we're playing with. Thank you very much.
So Ihab, tell us, share with all these people what you've done with the prize money. After I saw him at Oshkosh, I said, are you going to take a trip to Tahiti? And he
yes.
said no, and listen what he's done with this prize money.
So what we've done with the prize money is basically bought this computer over there so I can run SolidWorks, so I can do all the designs you're looking at, and we are funding the creation of prototypes that we can put into people's hands, basically loan them this thing and say, please try it out and give us feedback. The 3D printing is not cheap. It's economical, but not cheap. And what it does really is it gives us the flexibility to actually farm out some work when we don't really have time for it. So if we need to do some fancy machining and that's really sort of the blocking factor, just pay for it, right? So basically funding the creation of prototypes and putting them into people's hands. And so far, all the engineering work is volunteer. Certainly, I'm a volunteer here. I have many friends who are helping me out. They're also volunteers. And the work as it is, like the designs, are all online for free for anyone to look at. All the software is open source. The idea is not patent encumbered in any way. The hope is that people will just pick up on this and try it out and improve it. And if a manufacturer actually wants to build this, fine, I'm not against that. That would be like totally awesome. Anyway, thank you.
Hello. Question. My name is Lionel. I'm actually part of the aerobatic group that Ben's part of. Question, I guess, very beautiful way of graphically presenting alpha and beta size and that handle with that. The question that I got is do you have ways of compensating for varying, basically the red floor that you have? How do you dynamically compensate for things that would cause you to separate sooner rather than later, like contamination on the wings, icing, changes in flap conditions, and/or model-to-model airfoils.
Right. So the big thing is high lift devices, right? Flaps and stuff like that. And we have not done enough testing to know how to compensate for that. The easiest way is just have a flaps up line and a flaps down line. And that's just really simple. It works very well. That's just the white arc versus the green arc in airplanes. And just rely on the pilot to be aware of that. And that works. But maybe there are ways to do better. It's certainly an area of improvement. It is a worry of mine. Thank you for asking.
I have an obvious question, I think, for this group. My name is Mary, also with the same club. Has to do with aerobatics, and if you put it on any kind of aerobatic planes, like doing full multi-rotation spins, that kind of stuff, and if you could use it to really gauge, did you really let the plane fully stall before you start to spin, or any kind of fun scenarios like that?
My hope is that it would be useful for aerobatics. I think that's kind of my secret, in the back of my pocket thing. But since I'm not an aerobatic pilot, I can't make these claims. However, once we have a probe, please test it and give us feedback on whether and how it can be used for aerobatics. That's my dream, really. Thank you.
She flies a Russian plane, so.
Oh my goodness. Okay. Ooh. All right. Love it.
So my question is it intuitive with this device? Say if you were tossed upside down by wing turbulence, by looking at the ball, would the pilot know how to get back upright and flying again? Is it?
Right. So, no. And this is another area of improvement. See, there are two philosophies about these loss of control avoidance techniques. There's measurement, and then there's push to green. So the push to green idea is we're going to give the pilot this single arrow, this easy thing that says, do this and you will be okay. That's a little bit of a warning philosophy, but it does work for some things. The problem is that people tend to ignore warnings, and things that come up only during an emergency are not things that people are trained to recognize. The other side is measurement. So presenting something that shows them their data, even if the data is horrible, it still shows them the data with great fidelity. And that's something they can use all the time. Combining the two is an open question about which I have no feedback right now. I've certainly, this is definitely in the measurement domain, but there's probably work that could be done in the push to green domain as well, and maybe actually augmented. Please, send us ideas. Airball.aero.
I have a Citabria if you want to bolt it to my room strip too.
I would be happy to bolt it to your wind strip, sir. Thank you so much.
Thanks, Ihab. That's a great talk and a great idea.
Thank you.
So, I'd be interested in some kind of data logging capability, essentially some way to record yaw and pitch and, roll or whatever, and kind of replay my flight, at some point. And given enough storage, I guess it should be something that we can possibly implement, I think.
Absolutely. So this is a multi-part answer. Excellent question, thank you. This is actually, there are already people doing that for like your GPS tracks and stuff like that. And so if you merely add this information to your GPS tracks, you can then visualize it better. Actually, it turns out the second prize winner of this contest had something that he referred to as, I believe it was precise pilot, right? And his idea was basically to measure angle of attack and a few other variables and provide feedback to you, like grade you on your flight. Like, did you do an A flight or a B flight or a C- flight? So definitely, I think there's an awesome amount of work to do there. We would be providing the data, right? That's just all we know how to do. But
that is exactly what I was going to say, that by replaying your flight, you could see how close you got to the red line, so to speak, and
absolutely.
If you have instant bad habits, I think we picked up.
Yes, absolutely. Yes, I think that would be totally awesome. I agree.
So when you learn how to fly, you learn how to interpret instruments and how to react to them without having to think about what's actually going on. And the most obvious example is the ball. When you're not coordinated, you step on the ball.
Right.
So have you, in playing with your simulator, gotten similar sort of reactions to when you get close to a stall and so forth, where you don't have to process the information, you just know how to react to it?
So in the flying that I've done in the simulator, yes, I've gotten to the point where I sort of, so really what this is an artificial horizon for the wind, right? And you move your airplane relative to the wind. And I've kind of just become used to the fact that, yeah, I push down, the ball goes up, it grows, stuff like that. So the hypothesis is that, so obviously I'm biased, right? Because I came up with this idea, so I'm biased to say that it works. But the hypothesis is that this visualization will work for other people as well. And that's our hope, and that's why we're hoping to test it with more people.
We have with us Dave Morse, who was one of the judges of Founders Innovation Prize. So he got a chance to look at all 140 of the applicants. And Dave, is there any words you would like to say? I told him I wouldn't put him on the spot, but I thought having somebody who was in the background and saw everything that went on into this, could you give us a little insight?
Yeah, this was initially about 2 years ago when we started this. I'm on the safety committee that came up with the idea for the Founders Innovation Prize. And the goal was pretty lofty, and not sure that we'll ever achieve it, but if you don't try, you're never going to do anything. So we came up with the idea, and then the 5 judges got appointed, and we set a deadline of June for the entries. And a couple days before the entries, we only had like 6, and we're going, maybe this wasn't such a good idea. And then in the next 2 or 3 days, we got up to the 140 entrants, and so then they divided that up. And we didn't really know what to expect. We had 5 kind of bucket lists that we said that these are the 5 things that we hope that we'll see inputs to. And one was training, one's software, one's hardware, gadgets, and then we have a 5th column that it's what nobody had ever even thought of. And it was a huge success. We had some great ideas, but we're not there yet. And so this year what we've done is we've said that now it's a 5-year contest. And the people that won today, none of them have a mature solution that's ready to sell and ready to bolt into every airplane and is the final solution. So what we've done is we've recognized those 5 people and they won their award. But we've now continued the contest to say that the next contest, they're still eligible to re-enter. And what we want to do is see through the contest and through, now he has some good funding and has some inertia. He's way ahead of everybody else. But we're really looking for a mature solution that works and that everybody can apply to. Again, that's the applicability. So the contest is ongoing. So get to work.
Yes, sir.
Thanks, Dave.